So again, a potato spinning in space about an indicated point. I don't know if you're a fan of potato salad, but I like potato salad. I don't know if you're a fan of like diced potatoes at breakfast. I'm a fan of diced potatoes at breakfast. Let's imagine this potato has been cut up into lots of little pieces, but then reformed to make the original potato, with this being piece 1, piece 2, and piece 3. Right? If the whole thing is spinning with speed omega about this pivot point, then piece 1, which is a distance r1 from the pivot point, it has to be moving with a velocity v1. I'm pretty sure piece 2 is probably moving with a bigger velocity v2, it being further away from the pivot point. And piece 3, a third velocity in the middle of those two, it being further away than piece 1, but not as far as piece 2. So the kinetic energy of piece 1 would be 1/2 m1 v1 squared. And the kinetic energy of piece 2 would be 1/2 m2 v2 squared. And I think the kinetic energy of piece 3 would be 1/2 m3 v3 squared. All right. Now, obviously, we could extrapolate this for every single piece of potato until we get to the last piece of potato, 1/2 mn vn squared. Now, the potato isn't changing location, right? It's spinning in space, so it's staying put. But the pieces of the potato all have an individual kinetic energy because they are moving. Anything that's moving has energy. So if I wanted the total kinetic energy of the potato due to its spin, I would just have to add all of these kinetic energies together. Now, that's not a huge deal. If I get the potato out of the way, I'm going to have 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus 1/2 m3 v3 squared all the way until I get to the last piece of potato. This should give me the total rotational kinetic energy. Now, if the center of mass was moving as well, that'd be a separate thing, but I'm only talking about the fact that it's rotating. Now, one thing that all of these pieces have in common is they're all part of the same potato. So if the potato is rotating at one common omega, then I could rewrite each piece's velocity in terms of omega, since omega is a common value for all the pieces of potato. That would just require me subbing in for v how far away each piece is from the axis of rotation. So let's look at what that would do here. I would have 1/2 m1 omega r1 quantity squared plus 1/2 m2 omega r2 squared plus 1/2 m3 omega r3 squared, and so on and so forth for every piece. Are we good so far? Just going to reorder this a little bit if you don't mind and write this as 1/2 m1 r1 squared omega squared plus 1/2 m2 r2 squared omega squared plus 1/2 m3 r3 squared omega squared, and so on. Now, you do see that there's some common factors I can factor out, correct? Rather than rewriting it all, because I don't feel like it, that sounds like a job of a student, I could just pull out the 1/2 out front and the omega squared to the back, and I'm left with a sum in the middle that looks very reminiscent of something we've seen already before. Doesn't it look like it to you? Like, I could rewrite this as 1/2 the summation of m1 r1 squared from piece 1 to the last piece times omega squared, and say that this is rotational kinetic energy. For a smooth object, or an object that is of non-uniform density, I could write this as the integral of r squared dm from the first piece of mass till the entire mass times omega squared. Or, if you have followed this argument from the beginning and knew where I was going, we could write rotational kinetic energy is 1/2 I omega squared. And know from the very beginning of this derivation, since we started with the standard equation for kinetic energy, that this will be in joules. Rotational kinetic energy is a direct analog to translational kinetic energy. And it is based on the fact that individual pieces of the object are moving. So when we deal with the rotation of an object, its rotation has energy. And I don't think this is a stretch, but if you wanted to get something to spin, you would likely have to do work on it. Now, I don't think this is going to be a big stretch, and I'm not going to prove this to you. You already remember that the definition of work for translational mechanics had to do with a force and a displacement. Would it be too big a stretch to recognize that you could do work by applying a torque? It's going to produce the same thing, and the units would be the same. Top, we're going to get force times distance. Bottom, we're going to get torque times displacement, which will be in radians, which also gives us joules. So rotational work and translational work both can lead to either a change in translational kinetic energy or a change in rotational kinetic energy. But you can do both at the same time. Anybody who's thrown a frisbee or thrown a football has given an object both rotational and translational kinetic energy at the same moment. You can apply a torque and a force at the same moment, and therefore an object can have two different forms of energy at the same time. An object can have lots of forms of energy at the same time. So this is motion of the center of mass. So the center of the mass of the object is moving. It has translational kinetic energy. This is all rotation. If the object's facing in different directions, it's got energy. And it can have both at the same time. So any object that's rolling has two forms of energy at the same time. You throw an object, it has two forms of energy at the same time. It's going to have rotational and translational kinetic energy. Any object that is changing its position or changing its orientation can have both forms. I'm going to end right there because that's as far as we need to get for this.